Okay, so now what we talked about if we radiolabeled carbons 3 and 4, what would happen to them if they enter the TCA cycle in the last video. And we saw that if we radiolabeled the carbons 3 and 4 of glucose, they would end up on the carboxyl group. And because PDH, E1 on PDH decarboxylate molecules, or decarboxylates your pyruvate molecule at the carboxyl group, you're not going to have that carboxyl group enter your TCA cycle. So it's going to be lost as CO2 even before entering the TCA cycle. Okay, so that was the first one. Now in this video, what we're going to do is we're going to go over radiolabeling carbon 2 or 5, or if we radiolabel the carbonyl group right over here. Okay, so I'm just going to maybe erase some of these, and we're going to radiolabel carbons 2 and 5. So let's just say we radiolabeled carbon 2, and it's going to be our carbonyl on pyruvate. And now what we're going to do is we're going to go through the TCA cycle and see what happens to the carbonyl. Okay, so this is the other case we could have. Okay, this is the second example. So right over here, what we're going to do is we're going to radiolabel again. We're going to radiolabel over here. And as we saw in the previous video, you can count the carbons to see what's the difference between the reactant and products, or between acetyl-CoA, or between pyruvate and acetyl-CoA. And again, the carbonyls, they line up with each other when you count the carbons. Okay. And now all we're going to do, and this is the key idea, is we're combining a 2-carbon acetyl-CoA with the 4-carbon oxaloacetate. And this, I always say to the students, is that there's only 2 key areas that you have to understand, and then carbon tracing becomes very, very, very easy. Okay, so the 2 key areas that you have to understand are right over here. Okay, that's the first area. And then the second area you need to understand is right over here. Okay, so when we're looking at the carbon tracing, what we're doing is we have like these 2 different steps that we need to account for, and then everything else becomes straightforward. So let's go to the first one. So over here we have citrate synthase, and what it's doing is it's combining a 2-carbon acetyl-CoA with the 4-carbon oxaloacetate to form a 6-carbon citrate. Okay, so now if you look at oxaloacetate, we're just looking at oxaloacetate, you can see by this picture, like this drawing over here, that the color coding, it looks like these 4 line up with these 4, and that's totally fine. You could follow the color coding and stuff like that. But I thought it would be more helpful to explain why this works the way it does, just in case you get a TCA cycle on your exam that is not colored in, and you have to like kind of look for it yourself, or maybe the structures are flipped, or maybe the colors are thrown off a little bit. I don't know. But I want you guys to understand what's actually going on, so that you don't have to rely on the color coding to like figure out where the 4 carbons are from oxaloacetate. Okay, and the way that you do it, and this is the key, is all you have to do is remember oxaloacetate has these 4 carbons, right? So if we're trying to superimpose oxaloacetate onto citrate, you can superimpose it 2 different ways. You can either superimpose it at the top, right, like this, or what you could do, if I just took different colors, so if I do this, you can superimpose it like this at the bottom for it. Okay, so there's 2 different ways you could do it, and of course you could look at the color coding again, but the key thing here I want you guys to look at, and this is the key to understand where the carbons go, is you have to look at the alcohol group on citrate. Okay, so remember, aconitase is this isomerase where we're basically taking the OH group and we're moving it to one side of isocitrate. Okay, and it's very important that you guys look at the OH group and see where that goes. If it goes down, so in this case, notice how our OH group moved down from citrate to isocitrate. If the OH group, that signifies the carbons from oxaloacetate. So this is the key rule that I want you guys to take away from this. OH group moves to side of oxaloacetate, okay, in isocitrate. Or you don't even need to say in isocitrate. But yeah, the idea here is that you're going to look at isocitrate, and whichever way that OH group moves, that's going to tell you which 4 carbons are from oxaloacetate. And the reason why this works the way it does is, I know citrate kind of looks symmetrical, and you're going to say, well, how can the enzyme tell the difference? Because there's 2 CH2 bonded to carboxyl groups and stuff like that. But remember, all of these molecules, they exist in 3D space. So you could think of it like kind of like the 3 prongs that like are bonded to that central carbon. They can bind in only one specific orientation. And because again, enzymes have like this physical and physical and chemical complementarity. It's only going to bind in one specific orientation so that in aconitase, the OH group will always move to the side of the carbons from oxaloacetate. So what this is telling us is that if these 4 carbons are from oxaloacetate, and remember, you could have either put it as the top 4 carbons in citrate or the bottom 4 carbons in citrate, we're going to say that because the OH moves down and the OH, whichever way the OH move groups, or whichever way the OH group moves, those are going to be the carbons from oxaloacetate. Okay, so that means that these 4 carbons are from oxaloacetate. Now, I definitely wanted to mention this because I have seen examples in the past where, or previous versions of the worksheet, I think, used to have the OH group move up, right? And then because the OH group moves up, that's telling you that these 4 carbons are instead from oxaloacetate. So it's very important that you guys look at where the OH group is moving and not just memorizing that the top 2 carbons are from acetyl-CoA, okay? So that's how we're going to look at it. So again, you could follow the color coding, but I think understanding that the OH group always moves to the carbons from oxaloacetate helps you see what's going on. Okay, so now we know that the bottom 4 are from oxaloacetate, and we're now combining the 2-carbon acetyl-CoA with the 4-carbon oxaloacetate. So that means that these 2 carbons over here are going to be from acetyl-CoA. Okay, now the way that you know which carbon is which from acetyl-CoA, because remember, acetyl-CoA has 2 carbons and we have 2 carbons here, you can do it the way where you're looking at it and say, oh yeah, this carbon right here, the carbonyl, has more bonds to oxygen. This one also has more bonds to oxygen, so they're probably the same thing. Then this one has more bonds to hydrogen. This one has more bonds to hydrogens. And those are the same thing. That works perfectly fine. Another way that another student mentioned to me is you could count the oxidation state, because this carbon over here has 3 bonds to a heteroatom, whereas this one doesn't have any bonds to heteroatom. That works perfectly as well. But whatever you do, just keep it consistent. Find a method that works for you. There's always, as you've seen in this class, there's multiple ways of getting through the problems in this class. So find a way that works best for you and just keep consistent, okay? So now what we're going to do, okay, we're going to see over here again that our carbonyl, because that one has bonds to oxygen, it looks more like this one. So if we're looking at if we radiolabeled our carbonyl group, that's going to be this group right over here, this carbonyl group over here. And maybe I should change the color so that they don't overlap, so that's a little bit easier to see. So I'm just going to continue along with that labeling that we had over here. And now it's easy. We now know it's at the top, stays at the top, stays at the top, stays at the top. And now we get to that second key area, okay? Now, it's a little bit hard to see, and it's a little bit like, for the first time you think about it, it's going to be like a little bit complicated. But what I want you to do is, remember, here, how about this? Look at succinate, okay? Ignore that the box I drew around the carboxylic acid group, okay? Ignore that and just look at, here, let me maybe erase it. Just look at this molecule. You can kind of see how this molecule is very, very symmetrical, right? If you look at it like this, right? If I rotated this molecule, right, on its own, would you be able to tell that I rotated that molecule? Well, you're going to say, well, actually, the CH2 group is still bonded to another CH2 group, and then this one's also bonded to another CH2 group, and it's very symmetrical. So the idea here is that because these CH2 groups are kind of, the molecule itself is kind of symmetrical, and when we go to that next step of fumarate, if you look over here, this is now going to make it planar, right? So when we're going to be adding an OH group to this molecule with fumarase, okay, it won't be able to distinguish where it wants to add the OH group. It could either add it to this side, or it could add it to this side. So it could either add it same thing like this. It could either add it to this side or this side if we're working back a step, right? So the idea here is that because we can add the OH group to either side, what's going to happen is that our signal is effectively splitting. And I'll explain what splitting means in a second. But the idea here is that, okay, so now we have a radio label here. You can't really tell the difference between the top carboxyl group and the bottom one. So that means that we're going to have a 50-50 split over here, then a 50-50 split over here, 50-50-50 split. And if I erase this thing right over here, we're going to have a 50-50 split over here. Now, the only thing I wanted to add to this, again, and remember, the percentages are specific to what you're starting out with. The worksheet example, we only have 50% going through the pyruvate dehydrogenase reaction, and then the other 50% is going through pyruvate carboxylase. So if we are starting out with 50%, right here, it'll be 25 and 25. But I'm just giving an example where we're just 100% is going through PDH and through the TCA cycle, okay? So we're going to get it to split 50 and 50 because over here we're just starting out with 100. So let me just be a little bit more clear, okay? So common mistake that students make is, I just want to talk about that signal splitting. A common mistake that students make is they get asked this question. They say, okay, what does it mean for the signal to split? So I've heard a lot of different answers from students over the course of like these last few quarters that I've had the pleasure and honor of TAing this class. And some people say, oh yeah, when I'm saying that the signal splits, it means that I'm gonna have, I'm radio labeling these carbon molecules. So if I'm looking at this carbon molecule over here, I've seen that some people say that when I'm splitting it 50-50, it means that I'm gonna only have half of this carbon molecule over here. So I'm just gonna draw like half of one. So if this is like radio labeled, it'll only be half radio labeled over here. And then and then they say like the other one is gonna have the other half. So like maybe like the top half of the carbon. But you remember, we can't be actually splitting an actual atom, right? That doesn't make sense. So what it means for a signal to split is it's talking about a population of molecules. So when I'm saying that the signal splits, and what we're saying is that if I'm drawing a bunch of these molecules, so let's say, maybe I could just draw out a few of them. So if I'm talking about a population of molecules, and maybe I could actually save myself some time, and I could just copy and then paste this. And then copy and paste this, and then copy and paste this. I don't know why I'm copying each time. I could just keep pasting. But the idea here is that what we're saying is that in the population of these succinate molecules, half of them will have your radio label on the top carbon, and half of them are going to have the radio label on the bottom carbon, okay? And of course, at this point in time, it doesn't really make sense to say that because they look symmetrical. But once you add that H2O molecule or that water molecule, then it's going to pick a specific carbon that it's going to add its OH group to. And then you're going to be able to tell the difference, because for one of the molecules, the radio label will be one carbon away. It'll be directly next to that OH group. For the other one, it'll be 2 carbons away, okay? So what we're doing over here is we're just setting up like the idea that at succinate, because it's symmetrical, the enzyme's not going to be able to determine the difference between the 2 carboxylic acid groups. So if I, let's say, had radio label here, I'm not going to have 2 radio labels on one molecule. I'm going to have then radio label here on the next molecule. Then if I had radio label on this one, on this molecule, or maybe I should just go in order. But if I had radio label on this molecule, okay, not molecule, on this carbon, then I'm going to have radio label on this carbon. So then if you look at the population of these succinate groups, notice how if we're just looking at it like this, or maybe, yeah, if we're just looking at it like this, 2 of our 4 molecules, 2 out of the 4, or 50%, are going to have the radio label on the top carboxylic acid group. And then the other 2 out of the 4, they're going to have the radio label on the bottom carboxylic acid group, okay? So the idea here is that you're not physically splitting a radio label, you're just looking at the population of these succinate molecules, and on average, 50% of your radio label is going to be on the top one, 50% is going to be on the bottom one, okay? So I hope this made sense, and I'm going to make the next video on carbon tracing, or actually, I still haven't finished this carbon tracing, so let me finish that, and then we'll make the next one on radio label, tracing your carbons through carbons 1 and 6, okay? But I hope you understand what that means when you're splitting the radio label, okay? So now we went through this already, and we put the 2 carbon and 4 carbon acetyl-CoA and oxaloacetate together. We went through the TCA cycle, and then we noticed that our signal split at succinate. And now we're going to get a 50-50 mix on oxaloacetate, okay? Now what we're going to do is we're going to go through the next cycle to see what's like the ultimate fate of these carbons, okay? And now, again, we're combining the 4 carbon oxaloacetate to the 2 carbon acetyl-CoA, and the way that you know which ones are the carbons of interest for yourself is you have to look at the OH group. In this case, the OH group moves down, and we said that the OH group always moves to the side of the carbons from oxaloacetate. So again, we see the OH group moves down. So we know that these 4 carbons are, again, these 4 carbons, okay? So all I'm going to do is I'm going to superimpose that onto one another. So I'm going to maybe just erase this right over here. And maybe for this case, what we're going to do is so if we made this one our first cycle, we'll make this our second cycle, okay? Now what we're going to be doing is we're going to combine those two again. And the key idea, a lot of students make this mistake, is they think that we're combining another radiolabeled acetyl-CoA with a radiolabeled oxaloacetate, but that's not what we're doing. We're just trying to see where our radiolabel of interest that we've been following up to now is going to go. So we're going to combine it with another unlabeled acetyl-CoA. Okay, does this make sense? We're going to, of course, well, I'm asking a rhetorical question, but because you guys can't probably talk on YouTube, but the idea here is that we're going to combine an unlabeled acetyl-CoA with a radiolabeled oxaloacetate, okay? And we're going to try to see where our label of interest is going to end up, okay? And again, because the alcohol group moves down, we're going to say that these, or maybe I should draw the triangle to keep in mind, these 2 carbons, they're going to be 50-50. They're going to be from oxaloacetate. And then we're going to continue on. We're going to keep going forward. So again, we're going to go to these 2 carbons over here. Okay, and 50-50 as well. And now what we're going to do is we're going to get to the step isocitrate dehydrogenase. And the key idea here is that we have a leaving group right over here as carbon dioxide. So we have to see which carbon we are losing. So I'm going to erase the previous cycle. So the squares are the previous cycles things. So hopefully you can just rewind the video if you need to see that again. But I'm just going to erase it so that we can track the carbons and see what's going on. Okay. So now we're on the green ones, and we're just trying to see where they end up, okay? So anytime you're not sure, I always said you can count the carbons and compare the picture before and after. Notice how both of these are the same at the top, so I'm just going to start counting my carbons from the top, and we're going to go like this. We're going to go 1, 2, 1, 2, then we're going to go 3, 3, and then we're going to notice how there's something missing next to the 3, but we're going to keep going, okay? We're going to go to 4, and notice how they both have an oxygen bond to it. And then we're going to go to 5, which is the carboxyl group, okay? Now notice how we're missing that CO2 group that was, or the carboxylic acid group that was connected to carbon 3. So what happened is that middle carboxylic acid group was lost as CO2. It was oxidized to form CO2, and it's lost on this isocitrate dehydrogenase step. So what happens is we lose 50% of our label on this step, okay? So what's happening is we're losing this label. So all we're left with is this 50% that's left on our alpha ketoglutarate, okay? So now what we're going to say, and this is a common mistake students make, when they see the alpha ketoglutarate molecule, they're going to say, oh, I can just redistribute the percentages back to 100. So what they would do is they would do this and say, oh no, this is now 100. But no, for the purpose of this class, you can keep the percentages the way they are. You don't have to complicate it. Just if you're losing a carbon, you don't have to ever redistribute the percentages. Just keep them the way they are and just keep going on like that. So we're going to keep it as 50% like this, okay? And now what we're going to do is we're going to go to the next step, okay? And now I'm going to, again, count the carbons. We're going to go 1, 2, the same thing, okay? 3, 4. And then notice now that 5th carbon is lost. So what I did is that 5th carbon right over here, we're going to lose that one in the next step on alpha ketoglutarate dehydrogenase. So if we're putting everything together, notice how we lost 50% here, 50% here. We no longer have any more radiolabel, so we're done. So we lost 100% of our radiolabel on the second cycle. And going back to this table over here, notice how we said 100% will be lost by IDH and alpha ketoglutarate dehydrogenase on the second cycle, okay? Now again, I want to emphasize, and I hope no one just glances over this video and just goes through it too fast. The percentages depend on what the problem is asking you. So on the discussion worksheet, we only had 50% of it go through pyruvate dehydrogenase. So that means that we would have started with, if we were going to do that, we would eventually ended up having 25, because it splits over here to 25 and 25. Once we got to our second cycle, we would have again had 25 and 25 here. So we would have lost a 25% on each step from isocitrate dehydrogenase and alpha ketoglutarate dehydrogenase for a total of 50%. So make sure you're following along with the percentages and the guidelines that are given to you in the problem. I'm just giving you a general example that if we're starting off with 100% of our radiolabel going through the TCA cycle on the carbonyl carbon, Okay, we're going to see it split 50-50 on succinate on the first cycle. And then once we go through the second cycle, we're going to lose 50% each on isocitrate dehydrogenase and alpha ketoglutarate dehydrogenase, so that we lose 100% of the label as CO2 on the second cycle.